Hello everyone, my name is Donglai. I'm a doctoral student at Harbin Institute of Technology. It's a great honor for me to introduce our research finding to you on behalf of our project team. The title of the paper is Downlink Power Allocation Strategy in Multi-Antenna UltraDense Networks based on Cooperative Game. I will introduce our work from the following 6 sections. Firstly, I will introduce some background information about this topic. Then give the system model. The non-cooperative game model is formulated and the power allocation algorithm are introduced in the fourth section. At last, give the numerical results and conclusions. Okay, let's begin with the introduction. UltraDense can effectively improve the network capacity by densely deploying the various small cell base stations in the service area of microcells. Since the network architecture is fairly complex with the flexible, almost random deployment of small cell base stations, interference management for UltraDense becomes an important issue to be resolved. It has been investigated that efficient power allocation strategy can greatly mitigate interference and improve system throughput. However, there are still some shortcomings in the research work obtained. First of all, it remains unclear about the gap between the NE points of game models and the global optimal solution of original optimization problems. Secondly, no interference power constraints has been adopted to guarantee the QoS of key users. Besides, the convergence of proposed iterative algorithms are not proved theoretically. Last but not least, the system model are too simple. It's assumed that the base stations are equipped with a single antenna. The objective of the paper is to solve these problems. In this paper, we investigate the downlink power allocation problem for spectrum sharing multi-antenna UDN. The main contributions of our work are as follows. We use the cooperative game theory to design an iterative dynamic pricing power allocation algorithm, which converges to the NE of the game as well as the stationary point of the original SE maximization problem. As interference power constraint is applied to guarantee the QoS of the key user. Approximate power allocation algorithm is also proposed, which aims to reduce the signal overhead and improve the result utilization. Next, I will describe the system model. Consider a spectrum sharing UltraDense small cell work, where the small base stations are equipped with antennas. The distribution of base stations and users are modeled as independent, homogeneous point-to-point processes. Each user is associated with a closed small base station, and each small base station serves one user at each time slot. At the time division, multi-access is adopted. Although there is no intra-cell interference, the severe inter-cell interference limits the system capacity. The interference links are described in Figure 1. The power allocation strategy is divided into 2 levels. At the system level, the total transmit power of a small base station is allocated under the limitation of the maximum transmit power. At the cell level, the small base station allocates the transmit power for each antenna. In this paper, we focus on the system level. As for the cell level, the maximum ratio transmission is adopted. Under the above framework, the SNR of user of small cell n can be donated by equation 2. Then the optimization problem of maximizing as system SE can be expressed as problem 1, where Q is used to limit the aggregate interference received by the key user. Obviously, problem 1 is non-convex, so it's a challenge task to obtain its global optimal solution. The model of a cooperative game will be adopted to decouple the problem into several convex sub-problems in the next section. In this section, the non-cooperative game model based on dramatic breathing is formulated. We model each small base station as a self-interested game player. The non-cooperative game can be denoted as game G. The game player power strategy, utility function, and dynamic press are defined as follows. And the above cooperative game model, the problem can be decomposed into n-convex sub-problems. We can use the convex optimization method to find the global optimization solution of problem 2. Once the NE is reached, no player will attempt to change its strategy. Each NE of game G is a stationary point of the non-convex problem 1 and vice versa. As we know, the global and local optimal solution must be stationary points. Therefore, by finding the NE, we may obtain the local optimal solution of the original problem, which is the global optimization solution, if we are lucky enough. In the fourth section, the power allocation algorithms are proposed. Since the individual utility function and the constraint set are convex, problem 2 is a typical convex optimization problem. The Lagrange dual function of problem 2 is given by 12. As can be seen that the strong dual condition is satisfied. The duality gap is 0. By solving the KTT condition, we obtain the optimal solution of the original problem. The DPA algorithm is designed based on broad analytical solutions, as shown in algorithm 1. In each iteration, given the current power vector, each small base station computes its optimal transmit power, then updates the transmit power vector and the small step size. The NE of game T is obtained until the termination condition is satisfied. Based on the theorem 1, the transmit power vector converges to the NE of game G. Therefore, based on the DPA algorithm, we may obtain the local optimal solution of the original problem, even the global optimal solutions. In order to reduce the signaling overhead, the ADPA algorithm is proposed. The iterative processes of ADPPA is the same as the DPPA algorithm, except adopting the approximate channel power gain model uses the approach the ADPP algorithm. Each small base station only requires the transmit power of other small base stations and the channel power gain between each small base station and its own user. Next, the numerical results are given. The main simulation parameters are shown in Table 1. The performance of proposed algorithm are compared with the penalty effects-based power allocation algorithm and the non-uniform pricing-based power allocation algorithm. We set the average SE of each small cell as an indicator. The results in Figure 2 are obtained by the Monte Carlo method. We can see that the average SE of each small cell achieved by the proposed DPPA algorithm is the highest, and the performance of the proposed ADPA algorithm is better than the benchmark. Moreover, the performance of algorithm hardly changes with the density of base stations, which is counterintuitive. The dense deployment of base stations makes the average coverage area of each station smaller, and the distance between the base station and the user is closer. Therefore, the negative effects caused by the severe interference is cancelled by the strong signal. Figure 3 shows the convergence performance of different algorithms. Although the convergence speed of the DPPA algorithm is slightly slower than the PFPA algorithm due to dynamic pricing, the average SE of each small cell obtained at the convergence time is higher. The ADP algorithm has the similar performance with the DP algorithm, since the solving processes of the MPP algorithm don't require iteration as a horizontal line in the figure. Figure 4 shows the effects of the number of antennas on the performance of power allocation algorithm. As is shown, the algorithm SE of each small cell achieved by algorithm is improved with the increase of M. The reason is obviously because a large antenna number increases the density gain. It's shown that the proposed DPP algorithm has the best performance, and the ADPP algorithm outperforms the benchmark algorithm when M is less than 10, which means that the proposed approximate algorithm is more suitable for the case with a small number of small base station antennas. Figure 5 shows the average signal overhead required for each small base station per iteration of the proposed algorithm. It assumes that transmitting a float number needs 16 bits. It has been seen that with the increase of base station density, the signal overhead of the proposed DPP algorithm increases significantly, where it increases slowly for the ADP algorithm. Okay, let's make the conclusion. In this paper, distributed iterative downlink power allocation strategy were investigated for a spectrum sharing UDN with multi-antennas. Resolving the game theory, the non-cooperative game model was adopted to decouple the non-convex system SE maximization problem into several convex sub-problems. The Germanic pricing design guarantees that each NE of the game is a stationary point of the original optimization problem. Moreover, the interference power constraint was adopted for the key user. Under the game theory framework, we proposed the DP algorithm required global information and the ADP algorithm which is limited information. Simulation results show that the DPP algorithm outperforms the benchmark, and the ADP algorithm with a little performance loss can effectively reduce the signal overhead compared with the DPP algorithm. Okay, that's all. Thank you for your attention.